So, welcome back, and this is lecture number 42, and we will continue our discussion on vector spaces again. In particular, today we will be talking about the basis of a vector space and also the dimension of a vector space. So, just to recall from the previous lecture, we have seen that these vectors, the set of these three vectors 1 1 1 and 1 1 0, 1 0 0 and 1 0 1. These four vectors form a spanning set of R 3. The meaning was that any element of this vector space R 3 we can write as a linear combination of these four vectors. This is what we have seen in previous lecture with the help of this augmented matrix, which we can get out of this linear combination equal to this V 1, V 2, V 3, and from this augmented matrix, when we reduce to this row echelon form, we observe the following. What we have observed, that there are these three pivots. In column 1 we have pivot, in column 2 also we have pivot, column 3 also has a pivot, while the column 4 does not have a pivot, and this is what we call the free variable. So, the lambda 4 in our combination, when we have taken with lambda 1 with this vector, the given vector V 1, lambda 2 this given vector V 2. So, we call this V 1 V 2 V 3 and V 4, and this lambda 3 V 4 V 3 and lambda 4 V 4 is equal to this given vector V, which we have taken here, the V 1 and V 2 and V 3. So, with these system of equations, what we observe, that this lambda 4 is free variable, and meaning that we can assign whatever value we want to this lambda 4. So, now we have the flexibility to give this linear combinations here. So, choosing a different value of lambda, we have a different linear combination that will give us exactly this vector V 1, V 2 and V 3. So, this forms a spanning set, because any vector, any arbitrary vector we can pick from this R 3 space, and we can write down as a linear combination of these given four vectors. What is interesting here, that we have a non-unique representation because of this free variable. So, when we have a free variable, we can assign any value we want to this lambda 4, and then our representation of this given vector will also change. So, this linear combination will also change. What was also seen in the previous lecture, that if we do not consider, for example, this vector, the fourth one, if we do not consider this vector, that means we will not have this column here, this column we can delete now. So, in that case, this was the situation, and what we observe now for this case, that we have the every column has a pivot and there is no free variable, meaning when we do not have a free variable, we will get basically the unique representation, the unique solution of this system. And this is what we will discuss today, that having these three vectors, we have a spanning set, having these four vectors that also form a spanning set. Then we will come up with the idea now, that how many actually minimum vectors do we need, so that we can span the given vector space. So, for instance, in this case, we have observed that taking these three vectors, we can span the whole vector space, and also moreover the main point is that we have also the unique representation of the vector from R 3 if we take these three vectors, but if we are taking the four vectors, still it is forming a spanning set, but we are not getting a unique representation. So, keeping these facts in mind, now we will continue with the definitions of the basis and the dimensions. So, the basis is a linearly independent set that span a vector space. So, the simple definition, it is a spanning set because it should span the whole vector space V, but what is in addition that the linearly independent set. So, the basis is nothing but a spanning set which has all linearly independent vectors, that we call basis. Like in the earlier example, we have a possibility in this spanning set taking all those 4 vectors or taking only those 3 vectors, and but if we take those 3 vectors, we can easily figure out there those vectors are linearly independent, but having those 4 vectors in the set becomes linearly dependent. That also we can observe with the theory we have already developed in previous lectures. So, those 3 vectors, they are linearly independent, and for those vectors we can call that they will form a basis, not the 4 vectors, because 4 were also a spanning set, but that will not be the basis of R3 in that example. So, now the dimension. So, the number of elements in a basis is called the dimension of the vector space. So, here the number, how many elements are there, in that basis, that is called the dimension of the vector space. So, these two numbers are the basis, that is the set of the vectors, and that span the given vector space, and this number here which tells about the dimension of the vector space. Both are very important. Just a note here that every vector in V can be written uniquely as a linear combination of the basis of vectors, and this fact also we can explain from the previous example itself, that when we have the basis there, the basis means you have linearly independent vectors, and when you have linearly independent vectors, there will be no free variable when we talk about that linear combination of the given vectors to represent a vector from this V. So, that representation will be also unique whenever we have the basis, our spanning set is having linearly independent vectors, then the representation will be also unique. And the vector space 0. So, this is a special case when we have only one element, that is 0, and we define this dimension as 0. Okay, so let us take the example here, the vector space Rn, which we have already studied. Now, we will talk about what are the bases of Rn and what is the dimension of this vector space Rn. So, we consider these vectors now, a very special vector which we call the standard basis of Rn. So, consider these vectors. E1 is denoted when the first component is 1, all other components are 0. E2 is the first component 0, the second one, all other 0, and in En we have this nth component as 1 and all other components are 0. So, in this way we have defined these elements are from Rn, of course. So, now we will notice here that these vectors are linearly independent first, that we can easily check out, and we have I think checked before as well. So, we have to just see that lambda E1, lambda 2 E2 and so on, lambda n En. When we set to the 0 vector, then we should get out of this that lambda 1 is 0, lambda 2 is 0, and all are this zeros, which we can easily see because of this structure here itself. We will get from this lambda 1 0, from here we will get lambda 2 0 and so on. So, this is trivial to see that these set of vectors form a linearly independent set. So, all these vectors are linearly independent. What else we have to observe? So, we are going to find the basis and the dimension of the vector space. So, for that we need a spanning set basically that can span any can represent any vector from our vector space in the form of these given vectors. So, whether here it is possible or not, we will check now. So, given these vectors here, n vectors are given, and now any element if we take from this R n. So, any this is R n. So, this is the element of this R n. So, if we take a general any vector from this R n and which we are calling here v 1, v 2, v 3, v n, then we can see that we can represent this vector with the help of these given vectors e 1, e 2, e n. The idea is again simple in this case, and that is what these are called the standard bases. So, this v can be represented as the v 1 times this e 1, the second component v 2 times e 2. Because of this special structure here, it will be multiplied by v 1, and nowhere else we will get anything at this place, because all other vectors have 0 as first component. For the second v 2, only the e 2 has 1 at the second place, all others are 0. So, naturally we will get just v 2 from this one at the second position, and so on. So, we can represent, or we have already represented here, any vector v from this R n as a linear combination of these given vectors e 1, e 2, e 3, e n. So, it satisfies all the properties of the basis. We have this is a spanning set, because we can span any vector of the given vector space in the form of as a linear combination of the given vectors, and also these vectors are linearly independent. So, they form the basis. So, we got a basis for this R n, this set of vectors here, this forms a basis for R n. And the dimension now, it is a number of these elements in this set. So, here we have e 1, e 2, e n, there are n elements, and we got therefore, this dimension here of this vector space is n. This example where we are talking about the vector space of all 2 by 3, or in general also we can discuss like for R by S matrices. So, for simplicity let us take this 2 by 3, but the idea we can extend for R by S matrices as well. So, here the vector space of all 2 by 3 matrices we are talking about, and if we consider these vectors here, the one at this position and all other positions are 0. Similarly, now at the second position is 1, all others are 0, and so on. We continue with this, we get these 6 matrices where this one is sitting here at the first position only in this matrix. In the second case, one is sitting here and all others are 0, and so on. With this special structure, again these are the standard basis for this vector space of this 2 by 3 matrices. We have already seen that this form a vector space in the last lecture. So, here we are talking about or finding the basis and its dimension. So, these vectors are linearly independent and span the vector space of 2 by 3 matrices. Why they are linearly independent? Again the same argument which we had in the previous lecture. So, if we call them vector v 1, v 2 and this v 3, here this is v 4 and v 5 and v 6, and again the same thing we do, that we take here this linear combination v 1, v 2 with this lambda 6 and v 6 is equal to 0. This is 0 matrix here. So, this is nothing but the 0 0 0 0 0 0. When we compute this lambda 1 v 1, lambda 2 v 2 and lambda 6 v 6, we will get a matrix here with lambda 1, this is lambda 2, lambda 3, lambda 4 and lambda 5, lambda 6 is equal to 0. And now comparing these entries there, we will get lambda 1 is equal to 0, lambda 2 is equal to 0, lambda 3 is 0, lambda 4 is 0, lambda 5 is 0, lambda 6 is 0. So, they are linearly independent vectors. So, these are linearly independent vectors. The second, we have to check that they span the vector space of this matrices 2 by 3. So, naturally they do, because if we consider any vector, any matrix from this 2 by 3 matrices, or the elements we call vectors only. So, anything we take here, for example 2 by 3. So, this is a general matrix from this space 2 by 3, and with the help of this given vectors we can easily expand in terms of like A should be multiplied to the first one now, and this B should be multiplied to the second one, and so on. If we continue this, so that is the representation now of this general vector from this vector spaces, and that shows that we can represent any vector from this vector space in terms of these given vectors, which are 6 in number. So, what is the conclusion? That these vectors form a basis for this vector space, and the dimension is nothing but the product here 2 by 3, or we have the 6 matrices. So, the dimension is 6, which we can generalize for R by S matrices also. The idea is same. Another example where we are talking about the vector space this Pn of all polynomials of degree less than equal to n. Again, this example we have seen that this form a vector space, and now we are talking about this set here 1 t, t square, and so on t n. So, these n plus 1 polynomials, right, these are n plus 1 polynomials we have taken, and we claim that this is a basis actually for P and T. And why this form a basis? The reason is again clear. We have to check that these are linearly independent, which we can check as we have done for other examples, lambda 1 times 1, lambda 2 times t, lambda 3 times t square, and so on. This will be set to 0, and this is only possible when all these lambdas are 0. So, naturally these are linearly independent vectors of P and T. The second, we have to check that any polynomial from this P and T we take, can we represent that polynomial with the help of these vectors. So, again here if we take any polynomial, let us say this A0, A1 t, A2 t square, that is a general polynomial we have in this space P and T. They are the polynomials of degree less than or equal to n. So, for instance, we have taken this general polynomial, and with the help of these given polynomials we can easily use this. So, A0 will be multiplied by this 1, and this A1 with this t here, A2 with this t square, and so on. So, that is a linear combination of these given vectors. So, we can represent any element of this set or this space here P and T as a linear combination of these given vectors. So, therefore, this set forms a basis for P and T, again which we will also come later on to more clarification. The bases are not unique. So, this is a set which form a basis, we are writing a basis. There can be other set which can also form the basis, like in the example of the first example which we started with, we had those 3 vectors which form the basis, and they were not the standard basis. So, we can also choose, for example, 1 0 0 and 0 1 1 for R3, and this 0 0 1. So, that will also form the basis for R3, and the example we have seen those 1 1 1, that was one vector, another one was 1 1 0, and the third one was 1 0 0. So, that was not the standard basis, but they were also the basis. So, bases are not unique, we can have a different sets. The main properties are the elements must be linearly independent, that is one property, and the second one should be that they should span the whole vector space. So, here we have seen that these are the basis for this P and T, and the dimension here, the number of elements in this basis, which is n plus 1 at present. So, we have the dimension n plus 1. Another example where we will revisit our problem here, Ax is equal to 0, this system of homogeneous linear equations, and we know that the solution set of a homogeneous linear system also forms a vector space. So, here the A was this one, this example we have already discussed before. With this A, and we can reduce it to this echelon form, row reduced echelon form, and which tells us that these x1, x2, x3, x4 by choosing, because we have free variables here. So, this is pivot here, there is a pivot, there is a pivot, but this column does not have a pivot, here also it does not have a pivot. So, we have to choose this x2 and this x5 as free variables. By choosing these two as alpha 1 and alpha 2, we can compute all other x1, x1, x3 and x4, and when we combine, we got this equation here, that x1, x2, x3, x4 are nothing but alpha 1 times this minus 2 1 0 0 0 and alpha 2 times this vector. So, what we observed, that with the help of these two vectors, we can generate the whole solution set of this Ax is equal to 0, because we need to just keep on changing these alphas, the numbers here, and for any alpha here, whatever we choose, this is the solution of Ax is equal to 0. So, all possible solution of this Ax is equal to 0 we can generate using these two vectors, and these two vectors, looking at them, we can easily identify that these are the linearly independent vectors, which we can formally also prove, with the help of this linear combination set to 0, and that will imply that those coefficients lambda 1, lambda 2 is equal to 0. So, these two vectors are linearly independent, and their linear combination we can generate any vector of the solution set. So, that means these two vectors form a basis, because that is a property of the basis. We can generate any element of this solution set with the help of these two, or as a linear combination of these two vectors, and these two vectors are linearly independent. So, they span the solution set, and these two vectors are linearly independent, and therefore, they form a basis. So, these vectors can the vectors that generate the solution are these and this, and these vectors are linearly independent. Therefore, these vectors form a basis of the null space. Yeah, remember, so we call this solution set, there was a special name which we call null space. This is a vector space which is called null space. So, these vectors form a basis for the null space of A, and the dimension of this null space of A in this particular case, it is 2, which is again has a name, it is called nullity. So, nullity is nothing but it is the dimension of the null space of A. There are some useful results based on the observations what we have regarding the basis and the dimension. So, let V be a vector space of this finite dimension n. So, the dimension of the vector space is n. Then any n plus 1 or more vectors in V are linearly dependent. So, that is another nice results. We are not going to prove all these results, but one can with the help of some simple examples, one can at least get some idea that how these results are true. So, here any n plus 1 in our example also, which we started with this lecture today, we had those 4 vectors, but they were linearly dependent, and that was a spanning set, but it was a linearly dependent set, therefore, it was not a basis. So, their vectors were 4, while we have seen that taking those 3 vectors, first 3 vectors that form a linearly independent set and also a spanning set. So, that was the basis. So, the vectors in the basis were 3 there for R3, and so if there are 4 vectors which span R3, they cannot be there cannot be a basis, because 4 vectors from R3 they have to be linearly dependent. This is the result here. So, any n plus 1 or more vectors we take in V, they must be linearly dependent. So, for a vector space whose dimension is n, we cannot get more than n linearly independent vectors. They will be linearly dependent if we take any n plus 1 or more. Any linearly independent set when n is a basis of V with n elements is a basis. Yeah, another beautiful result, that we do not have to worry about picking up the elements for the basis. We can take any n elements, but that set should be linearly independent. So, any set which has n linearly independent vectors, that will be a basis, because for the basis these will automatically will be the spanning set. We pick any n vectors which are linearly independent, that will be the basis. And any spanning set V1, V2, V3, Vn with n elements. So, again the same thing, it is a spanning set with n elements. So, that will be also the basis. So, if a vector space has finite bases, then all of its bases have the same number of elements. That is another beautiful result, that if we have the n number of elements in the basis, so whatever you have different set of bases, but they will have the same number of elements, because that is the n, that is the dimension. So, whatever basis we take, the dimension is n of the vector space, then there has to be n elements in the set. And the number of elements in any basis of a vector space is called the dimension, which we have already discussed. So, for instance, we take this example of 4 vectors, and they forms a basis of R4. The set this forms a basis of R4. While the note that the given vectors are linearly independent, that we can easily check they are linearly independent whenever we have such a space or a structure. So, all 1 and then these 3 ones, 2 ones and 1s. So, they form a basis which we have seen for instance in the case of this R3. So, this forms a basis because these are linearly independent, and we know that the dimension of R4 is 4. So, we do not have to check, we have to check that they are linearly independent and they are 4 in number, because the dimension of R4 also we know. So, if we have any 4 linearly independent vectors from R4, not only these 4 vectors, we can pick any 4 linearly independent vectors that will form a basis. So, here the given vectors, they are linearly independent, and then it has to be a basis because the dimension is 4 and we have these 4 linearly independent vectors. Consider these four vectors in this R3. So, if we consider these 4 vectors from R3, and we know the dimension of R3 is 3. So, when the dimension is 3, these vectors must be linearly dependent, they cannot be linearly independent, because if they are linearly independent, then they can form a basis also. If they are linearly independent and they span the R3, then they can be also a basis, but basis will have only 3 elements, not more than 3 elements. So, here we have 4 elements. So, definitely they are linearly dependent, which we can conclude from the dimension of R3, which is 3. So, this cannot have, the basis cannot have 4 elements in its set. Okay, so, the conclusion is that we have the dimension, which is the maximum number of linearly independent vectors in a vector space V, and the basis is a set of linearly independent vectors that span the vector space. So, these are the references here used for preparing the lectures, and thank you very much.